So, dear colleagues, it's a bit annoying for me to introduce myself, and I will speak on hypergraphs drawings without multiple self-intersections. So these are slides of a different talk, but on the same matter. And so these are interesting introductory pictures. They are relevant, but I think in this short talk I will not have time to explain why they are relevant. So let me, maybe I will mention papers on which this survey talk is based and mention authors of those papers. So I will tell you what is the Whitney trick later on in this talk, but high multiplicity Whitney trick was first discovered by Mabillard and Wagner in codimension 3 or greater, then by them, Sergei Avakumov and myself in codimension 3, and in metastable range by Mabillard, Wagner, and myself later on. And I think in this talk, I will only briefly describe relations or applications to counterexamples to topological Tverberg conjecture. And here you see a list of the authors, in whose paper that those counterexamples gradually appeared. So let me come to subject matter. The well-known strong Whitney embedding theorem asserts that any compact k-dimensional manifold embeds into 2k-dimensional case. So for such basic results, I will not give original references in this talk. I will only refer to surveys in London Mathematical Society lecture notes and in Manifold Atlas project. And the idea behind this result, actually this result does hold for one-dimensional manifold in the plane. It's obvious even without Whitney, but the proof of high-dimensional case can be explained in low dimension. The idea is to make a trick like that, right? Take a general position map of a circle to the plane, arrange that there will be an even number of self-intersection points, and moreover, we can assign signs to those self-intersection points. We can change our map so that the self-intersection point will split into pairs of different signs, like here. And then we can cancel those pairs by Whitney trick. So this is the Whitney trick in dimension 2. And in order to motivate higher multiplicity Whitney trick, of higher multiplicity Whitney trick, let me state the double Whitney trick lemma. So for the purpose of this short talk, we don't mind category, but formally we work in the PL category. A map from a disk to a ball is called proper if the preimage of the boundary is the boundary. And of course, a disk is the same as a ball. But just to provide intuition, by disk I call a lower dimensional ball, and by ball I call a high dimensional disk. So that let me present the standard Whitney lemma. It states that if there is a proper general position map of disjoint union of k-dimensional disks into 2k-dimensional ball, and if the algebraic intersection number is 0, then there is a proper general position map of the same disjoint union denoted by D, which coincides with the initial map on the boundary. and under which the images of disks are disjoint. So the meaning is like on the previous figure, the images of disks under F intersect, but the images of disks under F prime are disjoint. And mind you, this result is correct even for k equals 2, although other versions of Whitney trick are incorrect in codimension 2. For example, well, there is a well-known example of Kerver and Milner showing that other version of Whitney trick fails for 2 surfaces in 4 manifolds. So this is the classical Whitney lemma, and the purpose of this talk is to describe its generalization to 3 or more disks here. And that generalization naturally appeared in constructing counterexamples to topological Tverbert conjecture, first in the work of Mabillard and Wagner. So let me state the, well, maybe, yeah, let me state the multiple version of Whitney trick. So now D is the disjoint union of R disks. The dimension of each one is k times r minus 1. And the dimension of ball to which those disks are mapped is k times r. So in general position, the self-intersections of the image of D here consist of finite number of points. So this is a picture for 3 two-dimensional triangles in 3 space intersecting at a point. And this corresponds to R being 3 and K being 2. Sorry, K being 1. So analogously to low dimensions, we can define a triple intersection sign in this picture, or an R-tuple intersection sign of an R-tuple intersection point of this map. And then the R-fold algebraic intersection number is the sum of signs of R-fold intersection points, or more precisely, of R-fold intersection points coming from different components. Of course, the image of D1 itself may have R-tuple intersection points, but they do not count in this R-fold algebraic intersection number. So the lemma states that if this number is 0, then well, self-intersections can be removed. More precisely, there is a map F prime of D to BKKR, which coincides with F on the boundary, and for which the R-tuple intersection is empty. So let me illustrate non-triviality of this theorem by these 2 pictures. Well, the left picture shows a trivial case, and the right picture shows non-trivial case. So in this situation, we can take a section of our picture by one of the disks. Yeah, the 3 disks are the 3 figures, the 3 two-dimensional figures in this 3-dimensional cube. And of course, this corresponds to K being 1 and R being 0 and R being 3. So this illustration, well, all these illustrations fall outside the statement of this lemma, but still they are good illustrations. So in this situation, we can consider intersection of everything with this section, with one of those disks, say D3. And then everything what we need is to make the double Whitney trick in this intersection, right? So the intersection of this disk with the other 2 disks is just the figure like that, which appeared in the double Whitney trick, and we can remove the intersections. But things can be more complicated. For example, if we keep the curvilinear disk the same, but slightly change the quadrilateral disk to this one. Then we can see that the triple intersection will still be 2 points, but in the intersection with this rectangular disk, we cannot make the double Whitney trick because in this intersection, these points are not connected. They are in different component of the intersection. And that's what makes the situation non-trivial. Okay. So the reference for R equals 2 is, of course, the standard Whitney trick. The codimension 3 case is due to Mabillard-Wagner, and the codimension 2 case is due to that joint paper of 4 authors. Actually, the analog of that lemma for k equals 1 fails for multiplicity 3 or greater. And to explain this beautiful example, let me come back. Let me come back to that theorem and make some comments. Actually, this is not an assertion of concerning the map F. This is an assertion concerning the restriction of the map F to the boundary. Because this R-fold intersection number only depends on F restricted to the boundary. So actually, this lemma resolves the question of whether given map of the boundary of D to the boundary of BKR can be extended to a map without intersection of different components. And so in order to construct a counterexample, we only need to construct this map on the boundary and then extend it to the disks themselves in any way. And so the example on the boundary is formed by 3 circles shown here. Well, and this notation NJs, PJs is used in the proof, not in the construction. So shortly, this is a picture of 3 circles in 2 spheres. And if we extend them in any way, in any general position way, to 3 disks in 3-dimensional ball, then we obtain a counterexample. Yeah, I will omit the proof of this counterexample, but I do plan to sketch a proof, or rather to illustrate the idea of proof of the lemma itself. But before that, let me briefly mention applications to the topological Tverberg conjecture. So this has to be omitted. Yeah. By the way, I think you can see the hyperreference for this talk. So if you're interested in omitted material, then you can just look at the internet. Sorry. That's interesting, but has to be omitted. Yeah. Let me briefly illustrate counterexamples to topological Tverberg conjecture. So a theorem states that any 3D minus 2 points in RD can be decomposed into 3 groups, such that all the 3 convex hulls of the groups have a common point. And that's a Tverberg theorem, not a conjecture. And that's a particular case for R equals 3, for triple intersections. And the topological Tverberg conjecture for any R asserts that for any continuous map of the simplex of this dimension to D-dimensional space, there are pairwise disjoint faces of this simplex such that the images of those faces have a common point. Well, and these conjectures was raised at the end of the 20th century. It was considered a central unsolved problem of topological combinatorics. It was proved for R a prime by Baran, Schlossman, and Such, and then for R a prime power by Ozalin and Bolvikov. And it turns out that the conjecture is incorrect for R not being a prime power. And here I list papers which are important for the counterexample. So I think the most complicated part of the counterexample is the work by Mabillard and Wagner based on this Whitney trick. So let me describe the idea of proof of that Whitney trick. Sorry, just a remark before that. So yeah, of course, this Whitney trick have different cases, different dimension restrictions. And so the Whitney trick by Mabillard and Wagner has got dimension 3 restrictions. Then we were able, together with Avakumov, to relax that restriction to dimension 2 when knots appear, which is in some sense wonderful because it is known that some versions of Whitney trick fail for codimension 2 even for double intersections. And later on, independently, Mabillard, Wagner, and myself were able to generalize Whitney trick to metastable dimension restriction. That is to the case when the general position R-fold points have positive dimension and it's allowed to produce even stronger counterexamples to the topological Tverberg conjecture. Those counterexamples appeared in our joint work with Roman Karasyov and Sergei Avakumov. Well, these interesting things has to be omitted. So let me try to describe the idea of proof of that multiple Whitney trick theorem. Yeah, let me show once again the statement. I think I will illustrate the idea of proof for R when R is 3. That is, there is a disjoint union of 3 disks of dimension 2k, and they are mapped into ball of dimension 3k. The threefold algebraic intersection number of those disks is 0. Then there is another map coinciding with F on the boundary and such that the triple intersection of these disks under this new map is empty. So that's the statement. That's a different idea. That's it. Here is actually the statement recalled. And the idea, yeah, let me recall the above pictures. Like here, if the two triple points of opposite signs in the triple intersection are contained in one component of this double intersection, like in this picture, and here D1 is this curvilinear disk, and D2 is this curvilinear disk. So the intersection is a union of, yeah, let me draw it separately, an arc like this and an arc like that. So the double intersection, this double intersection is connected. So then we can cancel these 2 points by the double Whitney trick applied to this double intersection in f of d3. Well, of course, f of d3, yeah, and then f of d3 can actually be kept stable. If this double intersection is not connected, then before making this procedure, we have to make it connected. And this is done by an analog of double Whitney trick to f of d1 and f of d2. So shortly, yeah, and actually analogous surgery of the intersection, making it connected or highly connected, is well known. It was first applied by in a classical paper by Heffliger, then in later papers by Habegger-Kaiser, Zenzel, Repov, Mikhail, and Melichov. But still, application of this construction to triple and higher multiplicity intersections is non-trivial and is an important achievement of Mabillard and Wagner. So let me, yeah, I think in the remaining 5 minutes, I will only be able to show you the pictures. So here is the picture. The bold curve.
Well, so you have 15 minutes, no, not 5 minutes.
How much? 15 minutes. Very good.
You have 15 minutes, 15 minutes at least.
Very good, yeah. Thank you. So this bold curve shows the double intersection. And the idea is to make a surgery, that is to replace this union of two, the idea is to join these 2 points by a tube running along a curve L in this manifold Q. Q actually is the 3rd disk in this example. So we make this a tube, and the tube intersects the manifold Q, the 3rd disk, by a union of 2 curves. So in this situation, the double intersection is already connected, but the price for that is that we changed this disk to a disk with handle. What we need disks. So after this part of surgery is done, we need to make another part of surgery. Sorry, it's not shown in a picture. So yeah, I think I will show you at a different picture. Well, luckily I have the same file. Oh my goodness. I have the same file on a computer, and I can draw things on the computer. So here we are. So recall that this is one disk, right? So these 2 points are joined by, oh my, that does look that way, are joined by an arc, by a curve inside this disk. Or actually, well, we need to take an a curve joining not exactly these 2 points, but joining some close points in this disk. And then we can span a 2-dimensional ball by this new curve, by this curve joining the points, and one of the curves which are intersections of the tube and the third disk. And then, yeah, let me describe what happens. How do we cancel this disk? And I will first describe by different picture. So if we have the torus, the standard torus, and the meridian of the torus, and the disk in 3 space spanned by this meridian, then a surgery of this disk, a surgery of this circle in a disk makes the following picture. So what do? We take a neighborhood of this disk in 3 space, and we cut away this neighborhood from the torus, but glue to the remaining part the 2 disks which are in the boundary of that neighborhood. So these 2 disks are shown here, not a very instructive way, I'm afraid. So, but this is an example of a surgery canceling a circle by spanning it with a disk. And actually, analogous surgery has to be done here. So we take a neighborhood of this very curved disk in high dimensional space, right? And we cancel a handle of our handled disk by analogous surgery. That's the unpiping step of this Whitney trick, and after that, we both have the self-intersection. We both have the double intersection connected, and the manifold again a disk, but a different disk than the disk from the beginning. So that's a starting points of all constructions. Of course, when they generalize to other situations, generalizations already become different. And let me present the R-fold. Let me present generalization of the R-fold Whitney trick to the case when general position R-tuple intersections have positive dimension. As I told you, applications are stronger counterexamples to the topological Tverberg conjecture obtained in a paper by Avakumov, Karasov, and myself. So in order to state this generalization, I need some notation, very simple notation. First, recall that D is disjoint union of R disks of dimension k r-1. By B D times R, we denote a set of matrices D times R whose elements are in B. And delta R is the thin diagonal of D times R dimensional Euclidean space. So let me present a statement of the R-fold local disjunction lemma. And we have this dimensional restriction. There is a proper map such that there are no R-fold intersections on the boundary. And then the map F to the R from the boundary of this product. Of course, this is a map from this boundary to B D times R. But actually, this map misses the diagonal. because of this condition, this is actually a map to the complement to the thin diagonal. So it's clear that if there is a map F bar, which coincides with F on the boundary, and for which the images of the disks are disjoint, well, are fully disjoint, then this map R extends to the product of the disks themselves. Well, but the point is that theorem is that the opposite implication also holds. That is, if this map extends to the product of the disks, then there is a proper map from the same disjoint union to BD, which coincides with F on the boundary and such that, and which does not have R-fold points coming from different components. Well, perhaps I have to explain this statement and comment on it rather than give an idea of proof. So first, why it is a generalization of the previous theorem for the case when D is K times R. For this case, well, this dimension restriction reduces to codimension 3. This is automatic by general position. And this is a map from a sphere to a sphere. Or rather, yeah, of course, this space is not homomorphic to a sphere, but it is homotopy equivalent to a sphere when R is 2. Indeed, if we delete, if from R2 we delete the diagonal, then the complement is homotopy equivalent to the zero-dimensional sphere. And analogously, if we delete from RD the diagonal, then the complement is homotopy equivalent to D-1 dimensional sphere. So this is a sphere, and then this is a map from a sphere to a sphere of the same dimension, and then its extendability to the disk is equivalent to the degree of this map being 0, and naturally the degree of this map is counted by intersections with signs of the map F. So this is indeed a generalization of the previous R-fold local disjunction theorem. Second, it says that the abstraction to existence of such F prime is in a homotopy group of this space. So for R being greater than 2, this is no longer a sphere, a more complicated space, but there is an only abstraction in a homotopy group of this space because this is a sphere. And this is good. This means that this result can indeed be applied, and this property can indeed be checked. Yeah. I think I should comment on the proof of this result. Maybe first on the history. So, as references show, this result was claimed by Mabillard and Wagner in 2016. But I think that their proof is well, it has gaps, and the gaps are thoroughly explained in my paper. Well, I'm sorry that an update of that proof did not appear in those 4 years. But still, I do attribute this result to Mabillard-Wagner. I call it Mabillard-Wagner theorem in order to concentrate on mathematics, not on priority question. Well, as for mathematics, well, I already mentioned the reason why this result, well, why this generalization is not trivial. The general position R-tuple intersection points are no longer isolated points. They the set of such points has positive dimension, so we need to make surgery more complicated. We need to use induction, yeah? And in this induction, there appear some homotopy theoretical questions, which are, well, when it's not that hard when it's invented, but of course it's not easy to make a plan of this proof. And yeah, there are different approaches. Mabillard and Wagner used PL topology, which brought a problem of generalizing vector fields to PL situation. And one of the problems is that references for such generalization, they do exist, but they are written in a way which is hard to apply. In my proof, I used a different approach. I approximated this map by a smooth map, not by a PL map. And moreover, I approximated it by an immersion, not just a smooth map. And that allowed to use a smooth category where vector fields and things which are based on vector fields work very well. That allowed to use Pantregin construction. And I think, well, I would state a principle that deleted product is good, deleted joint is better, Pantregin construction is best. It's a very good way to handle homotopy theoretical problems arising in combinatorics. Here I stop. Thank you for your attention. Sorry. As a chairman of my own talk, I have to ask if there are some questions.
May I ask a quick question, please?
Yeah, please.
So first of all, I like this principle: deleted product is good, the deleted joint better, and Pantregin construction even better. So let me ask you a general question. You started with the picture of this icosahedron with the intersecting rectangles, and it is related to this bunch of theorem about emergence of the projective plane into the three-dimensional space. So my question is the following. What is the relation of Whitney trig elimination in this, let's say, more combinatorial category to elimination of, let's say, triple points in the case of emergence? Does it work in any direction? I mean, there are obstructions for removing triple intersections, let's say, if you deal with emergence,
yeah.
And here you have other obstructions. Is there any bridge between these constructions? Whatever that means, yes.
Well, I think in some sense...
let's say, how would you relate obstructions, cohomological obstructions?
In some sense, almost embeddings, that is, well, maps or Tverberg maps, right? They are the opposite. They are on the opposite side as immersions.
Mm-hmm.
So let me draw a picture. I think I can do it. There are just maps, there are embeddings, and there is something in between that, right? And so these are immersions, they are in between maps and embeddings. And there are almost embeddings or Tverberg maps, they are also in between, but in a sense, almost embeddings and immersions are the opposite. That is, immersions allow closed self-intersections, right? Sorry, immersions prohibit closed self-intersections. So only faraway points in the domain can be mapped to the same point in the image. While almost embeddings or Tverberg maps, they prohibit faraway intersections.
Mm-hmm.
That is, points in disjoint simplices cannot be mapped to the same point. And for this reason, of course, abstractions are analogous, but well, they are only analogous as different abstractions to different problems.
So you don't see immediate connection. I mean,
well, only philosophical one. There are different problems in mathematics, and one arrives at cohomological abstractions in those different problems, but nothing more than that.
Yeah, thank you.